Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Review Behavior of Infilled Walls Vishal Kr Gupta 1 PG Student, Muir University, Chittorgarh, Rajasthan, India Abstract Due to scarcity of land, extensions of existing buildings are becoming the necessity and requirement for urban development and rebuilding process. New extensions are added to the existing buildings to create additional spaces because of the functional requirements. Vertical extensions can often offer the most discreet and economical way of increasing the capacity of an existing building. Vertical extensions inevitably results in increase in the loading on the existing building. In such cases, strengthening work to structural elements such as columns, walls, and foundation becomes necessary. This report presents the analysis and strengthening aspects for vertical extension of an existing building. This is an actual extension project for a G+1 building along with a basement, situated in Rajpura, Punjab. The proposed extension is required to provide 2 additional stories which will accommodate a double-height multiplex along with other facilities. The structural analysis of the building is done in the STID-Pro software. For the proposed vertical extension of the building, 2 options for structural system have been studied. A. RCC beam column frame system with RCC floor and roof slab. B. Steel portal frame system with steel columns, beams, and RCC slab at intermediate floor levels. Roofing consists of steel truss with asbestos sheeting. Separate STID models of the building are developed for structural analysis of both the above options. A STID model of the existing building alone is also developed to analyze the loads and obtain the design forces sustained by the existing building. Average increase in vertical forces at base in comparison to design forces sustained by existing building alone is 60% for R.C.C extension and 23% with extension with steel structure. The increase in resultant moments is 66% for R.C.C extension and 28% with extension with steel structure. Results of the structural analysis indicate that the extension with steel portal frame system results in lesser increase in design forces and would require lesser strengthening of the columns and foundation. Hence the steel portal frame is adopted as the structural system for the vertical extension. The strengthening of the foundation is carried out by leveling the existing slope footing by PCC and laying a new foundation over this leveled surface. The column strengthening is done by providing additional reinforcement outside the existing column, and column section is enlarged by jacketing method. 1 Introduction. The purpose of buildings extends beyond merely providing habitat to people. Buildings should be designed in a manner which ensures security of their occupants. With structurally more secure buildings, people will feel more protected against unfortunate events such as acts of terrorism, etc. Hence, it is important to study the effects that blast loads can have on buildings. Blast loads are dynamic in nature, and can be calculated precisely, just like wind and earthquake loads. The foremost aim of this work is to discuss and analyze the performance of different structural systems under the impact of blast loads in events of explosions. The method for mitigating effects of detonation has been discussed, thus preventing harm to life, property, and equipment. Relevant literature has been studied thoroughly, with emphasis on topics like possibility of vulnerability evaluation, risk easing, developing ductility and structural response characteristics, etc. 1.1 Types of extensions. Although extension can be done in various ways depending on the requirement. Different types of extensions that can be done are as follows. 1.1.1 Front extensions. Extensions at the front of a building are normally restricted to small additions such as porches and vestibules. This is because front extensions are the most conspicuous and thus can radically alter if not destroy the character of the building. 1.1.2 End extensions. An end extension is a form of side extension. It can occur if a building is being elongated or where an extension is being installed at the gable of an end terraced block. In such circumstances, the available space for expansion is likely to be limited. However, extensions to single-story framed buildings such as large supermarkets or warehouses are often 2 or more bays in length because of the spare space. 1.1.3 Side extensions. In residential property, an attached garage often forms the main type of side extension. In other instances, the side extension may be required to provide an enlarged or additional room. More usually, however, a 2-story extension comprising, say, a garage on the ground floor and a bedroom on the upper floor forms the main type of addition incorporating these functions. 1.1.4 Rear extensions. These extensions are very popular in mid-terraced residential dwellings because of the physical site constraints. Moreover, the planning constraints are usually less stringent at this part of the property. 1.1.5 Corner extensions. As indicated above, front extensions sometimes form part of a larger side extension. This solution allows the front of the building to have a minor increase in size along with a larger addition at the side. 1.1.6 Combined lateral and vertical extensions. In rare cases, an extension may involve an enlargement of the property both horizontally and vertically. Load transfer. Distribution. Aspects of load transfer that should need to be considered include the effect of concentrated load on supporting elements, the effect of eccentricities on the supported and the supporting elements, design consideration and assumptions, the ability of reinforcement in concrete structures to provide adequate tying action. For robustness requirements, IJERT 10 is 060069 www.ijert.org 173. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 1.2 Background and scope. Vertical extensions can often offer the most discreet and economical way of increasing the capacity of an existing building. They are often formed either in the roof space or basement. Such changes are of course less obtrusive than lateral extensions. In many cases the only obvious signs of, say, most vertical extensions are upward because there is nearly always free space to expand in that direction. In contrast, downward vertical extensions are limited because of the physical restrictions imposed by the substructure and soil conditions. On rare occasions the latter type of extension may still be feasible if a basement is required in a very tight site. Moreover, because of their impact on the extra requirements for stairs and services in the building, vertical extensions are sometimes more complex than lateral additions. The main focus of this project was on strengthening of existing building in Rajpura, Punjab. This choice was based upon the fact that the project was carried out with support from Tech Pacific, a structural designing firm located in Mahilai, Punjab. Even if the methods discussed here are meant to be applicable mainly to story extension projects, it should also be possible to apply the results of this project to other types of situations where strengthening is needed. It should however be noted that the choice to focus on strengthening for story extension may limit the number of investigated strengthening methods. To literature review. To be able to make use of existing knowledge concerning story extensions, several reference projects have been studied. Information has been collected through research involved in story extension projects. The focus was on the structural solution for vertical extension and integration of the new structure to the existing structure. Was a large part of the project. The total area involved was 68,000 square meters. Figure 2.1 City Cronin. After reconstruction 2.2.3 Vertical extension in Husby. The existing buildings were built during the 70s. The buildings had 5 floors and its structural system is site-cast concrete slabs and precast concrete columns. The project involved vertical extension of 3 buildings and each building was extended with 1-story volumetric student study bedroom apartments. The project comprised 35 new apartments as shown in Fig. 2.2. The existing building was from the early 70s with concrete structural frame. Early in the project the client decided to use a highly prefabricated building system in order to minimize the disturbance to the surroundings. Characteristic of this vertical extension project was its high level of prefabrication. 2.1 Case Studies 2.2.1 Vertical extension in City Cronin. At the time the project was one of the big ongoing projects in central Stockholm and comprising 50,000 square meters refurbishment and extension as shown in Fig. 2.1. This vertical extension project was performed under the design and build contract model. The construction system was prefabricated steel columns and precast concrete slabs. The existing building was built in the 70s and its structural system is side-cast concrete slabs and columns. 2 houses in the block were merged together by the extension. The buildings were vertically extended with 2 and 4 floors. The project was characterized of high complexity. The complication of the foundation resulted in many uncertainties in the construction process. The just-in-time production philosophy was used in the project. 2.2.2 Vertical extension in Clara Zenith. The existing building is from the late 60s and was built with side-cast concrete slabs and precast concrete columns. The buildings in the block were extended with 1 floor and with 2 stories detached houses on top. The extra floor was built with side-cast slabs and the houses were made of prefabricated timber elements. Also refurbishment of the existing building. Figure 2.2 Husby project after reconstruction 2.2.4 Vertical extension in Brazilii Park. The building in the project Brazilii Park is placed in an area with many hotels, theaters, restaurants, and commercial buildings in the Nybro Bay in Stockholm as shown in Fig. 2.3. The vertical extension was on a theater hall, built at the beginning of the last century, which had already been extended with 5 floors during the late 60s. The project included demolition of 3 floors, refurbishment of the existing building and vertical extension with 4 floors. The theater and the original facade were to be conserved. The vertical extension structural system was a combination. Time was during the years 2000 to 2002. IJERT 10 is 060069 www.ijert.org 174. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Figure 2. 3 Outline of the Brazilii Park project after reconstruction 2.2.5 Industrialist building with light gauge steel framing systems. This research has studied the experiences from the Swedish industrial building process with light gauge steel. In the following section, 2 examples of projects using an industrialized building process with light gauge steel will be briefly described. KV Naktürgelen. As part of a research project, the Naktürgelen project was studied. Person, 1997, Anderson, Borg-Brandt, 1998. Its aim was to compare different building systems and processes with each other. The Naktürgelen project, KV Naktürgelen Phase 2, consists of 3 different phases. During the planning of the second phase, it was decided to build 2 identical buildings. 2 different building systems were used, whereby an analysis and comparison between the 2 building systems were possible to complete. A traditional concrete building system was compared with the industrialized building method of light gauge steel framing. 2.2.6 Vertical extension of Hotel Gothia Central Tower. Gothia Central Tower, located in central Göteborg, was built in 1984 and initially reached 62 m above the ground with its 18 stories. It consists mainly of in situ cast concrete with a big core in the middle of the tower for stability. Samuelson, E. January 24, 2013. Load-bearing walls between hotel rooms go downwards through the building except at the lower entrance and conference floors, where columns are used instead. The building is mainly founded on footings on top of the bedrock, but short end-bearing piles have been used in some places. 6 new stories are being added at the time of writing, giving the building a new height of 83 m. Some slabs and beams in the upper stories of the original building have been strengthened with carbon fiber reinforced polymers. The slabs were strengthened with regard to bending moment, and the beams were strengthened to be able to spread the high concentrated loads from the new steel columns that were placed on top of the beams near the edge. The anchorage of the new part was achieved by attaching post-tension steel plates to the upper core. These plates extend several stories downwards where they are anchored into the existing core. February 12, 2013. The old building lies in a steep slope, which means that all 3 stories are visible at one side of the building while the road on the other side of the building is in level with the roof of the old structure. 5 new stories were added in 2006. Many of the original columns were too weak for the extension and needed to be strengthened. This was achieved by section enlargement. Skelander, February 12, 2013. Stability issues were solved by a new stabilizing stairwell in prefabricated concrete and a new concrete wall that was installed at one gable. Elu, 2013. The wall was prefabricated in the added part, while the continuation of this wall in the old building was strengthened through section enlargement. 2.2.8 Vertical extension in residential building. Apelsin. An A-story extension is planned on a 4-story building located in Kungsbacka, 30 kilometers south of Göteborg. The original structure was built in 1976 with a load-carrying system of concrete walls mainly oriented in the transverse direction of the building. Johansson, January 31, 2013. The building is located on varying thickness of clay above bedrock, and 2/3 of the structure is founded on end-bearing piles, while the other end is founded on footings due to a shorter distance to the bedrock. A 2-story extension is yet to be carried out along with renovation of the apartments in the building. The structural design for the extension and its accompanying strengthening was carried out. No real weaknesses were detected in the building. Strengthening of the foundation will also be required, and extra piles are to be added and connected to the load-bearing walls through lintels. 2.2.9 Hotel Scandigribinen. Hotel Scandigribinen is located at Kungsportshavnen in central Göteborg. The original building was built in the 60s and consists mainly of in situ cast columns and beams. Jarlin, March 13, 2013. On top of the beams, prefabricated TT slabs are supported. The height of the original building varies, and the lower part contains 3 stories above ground plus 1 basement. At the time of writing, a story extension is being built on the lower part of the hotel. As can be seen in figure 2.45, new stories are added so that the extended part will reach the same height as the left part in figure 2.4. The new structure consists of steel columns and HSQ beams with hollow core slabs. Jarlin, March 13, 2013. To minimize the height of the beams, the steel columns stand with a spacing of 4 m, which can be compared with 12 m for the columns in the original structure. 2.2.7 Vertical extension in office building, etc. Bonniers Art Gallery. Bonniers Art Gallery is located in central Stockholm and was built upon an existing 3-story building. The original superstructure consists of columns, walls, and slabs of in situ cast concrete founded on footings on bedrock. Skelander. Figure 2.4 Section through Scandigribinen. IJERT 10 is 060069 www.ijert.org 175. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 3. Analysis and Design for Vertical Extension of a Building 3.1 Project Detail and Background. The present chapter deals with the analysis and design of an existing building in order to extend the existing building with further 2 more stories. The building is a commercial complex situated in Rajpura, Punjab. A proposal for extending the building was given by the owner of the building. The proposed extension is required to provide 2 additional story which will accommodate a double height multiplex along with other facilities. The existing building is 68.57 m long and 3.3 m wide. It is a G+1 structure along with a basement. The columns are spaced at 4.8 m and 6.2 m in longitudinal and transverse direction respectively. Each story height is 3.65 m. 3.2 Analysis and design methodology. The architectural design for the proposed extension has been carried out by M/S Incubis Architects, New Delhi. The structural analysis of the building is done in the STID Pro software. A STID model of the existing building is developed to analyze the loads and obtain the design forces sustained by the existing building. Separate STID models are developed for the analysis and design of the vertical extension and also to evaluate the effects of the structural model developed. 2 alternatives for structural systems have been studied for the proposed extension. A. RCC beam column frame system with RCC floor and roof slab. B. Steel portal frame system with steel beam/RCC slab at intermediate floor levels. Roofing consists of steel truss with asbestos sheeting. 3.3 Load combinations. The various load combinations considered for the analysis of the RCC structure are as follows: A. 1. DL and LL. B. 1.5. DL and LL. C. 1.2. EQX and DL, plus 0.6 LL. D. 1.2. EQZ and DL, plus 0.6 LL. E. 1.2. EQX and DL, plus 0.6 LL. F. 1.2. EQZ and DL, plus 0.6 LL. The various load combinations considered for the analysis of the steel structure are as follows: A. 1.0. DL and LL. B. 1.5. DL and LL. C. 1.2. EQX and DL, plus 0.6 LL. D. 1.2. EQZ and DL, plus 0.6 LL. E. 1.2. EQX and DL, 0.6 LL. F. 1.2. EQZ and DL, 0.6 LL. G. 0.9 DL plus 1.5 EQX. H. 0.9 DL plus 1.5 EQZ. I. 0.9 DL minus 1.5 EQX. J. 0.9 DL 1.5 EQZ. K. 0.9 DL and WL, in X direction. L. 0.9 DL and WL, in Z direction. 3.4 Specifications of new structure. The new structure consists of steel tubular sections/built-up sections and ISMC sections. The elevation of the whole structure showing existing RCC columns and new steel columns. The layout plan and sections of the new steel portals over the existing structure. The thickness of the deck slab is 75 mm above decking sheet. The decking sheet is used as sacrificial shuttering also. 4. Strengthening of existing building. 4.1 Strengthening of structural members. Strengthening is an improvement over the original strength. The need to strengthen slabs and columns came up quite often. Strength of the building is generated from the structural dimensions, materials, shape, and number of structural elements, etc. Due to the variety of structural condition of building, it is hard to develop typical rules for strengthening. Each building has different approaches depending on the structural deficiencies. In the design of strengthening approach, the engineer must comply with the building codes. The results generated by the adopted strengthening techniques must fulfill the minimum requirements on the building's codes, such as deformation, detailing, strength, etc. 4.2 Methods of strengthening. There are many relatively new technologies developed for strengthening. Some of the methods by which strengthening can be possible is as follows. 4.2.1 Strengthening with shotcrete. To minimize formwork and labor, shotcrete can often be a good substitute to conventionally cast concrete, when it comes to strengthening of concrete members. Shotcrete is basically an approach where concrete is sprayed onto the surface instead of being cast in molds. The process requires experienced workers if a good result should be achieved. There are 2 different basic ways to apply the shotcrete. The first method implies that the almost dry components are sprayed through a hose with help of compressed air. The water is then added in the nozzle. This approach is known as the dry method. Another way is to use the wet method, where the concrete is already mixed with water before it is pumped through the hose. The dry method is normally used for strengthening of concrete members, while the wet method is preferred for bigger projects, e.g. when tunnels are strengthened. 4.2.2 Strengthening with externally mounted steel. Regular reinforcement bars can of course be used in the added concrete, when performing a section enlargement on a member. There are however also other areas of application in which steel can be used to strengthen concrete members, for example by externally mounted sheets and profiles or as means to apply a pre-stressing force. Steel profiles can also be used to improve the resistance of structural members. These can be used for various kinds of members and be installed in different manners. IJERT 10 is 060069 www.ijert.org 176. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN 2278-0181 Volume 10 Issue 06, June 2021 4.2.3 Strengthening members with pre-stressing steel. Pre-stressing is primarily suited for strengthening members with regard to the flexural capacity. The most common application is to use it on beams or slabs. Pre-stressing of existing members functions in a similar manner as internal post-tension tendons without bond, but with the tendons, or single strands, connected only to the exterior of an already existing structural member by end anchors and deviators. Deviators are used to change the angle of the tendon to acquire a better utilization of the pre-stressing. Since it is at the deviators and anchors that the forces are transferred to the concrete, it is not possible to follow the moment curve in the same way as with internal tendons. 4.2.4 Strengthening with fiber-reinforced polymers. Fiber-reinforced polymers, FRP, is a composite material consisting of fibers surrounded by a polymer matrix. The matrix is what keeps the fibers together and transfers the forces between the individual fibers. Different materials can be used as matrix, but one that is epoxy-based is most commonly used. At present, strengthening of concrete structures with FRP composites is not treated in the Eurocodes or any other standards. Designers who use FRP strengthening are therefore referred to available handbooks or material manufacturers. However, the structure needs to be evaluated, if it is appropriate for FRP composites before any FRP strengthening measures are taken. Figure 4.2 Reactions after existing foundation. 4.3 Strengthening of foundations. The reactions for the existing foundation and reactions after the extension are shown in Fig 4.1 and Fig 4.2 respectively. The foundation layout plan is shown in Fig 4.3, which shows existing foundation and foundation after the extension. The foundation with hatching shows existing foundation represented with F, while foundation represented with NF shows new foundation which is provided for the extension. Figure 4.3 Foundation layout plan. Figure 4.1 Reactions for the existing foundation. Figure 4.4 Dimensional plan of foundation showing strengthening. IJERT 10 is 060069 www.ijert.org 177. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 C. Lateral support to all the longitudinal bars shall be provided by ties with an included angle of not more than 135 degrees. D. Minimum diameter of ties shall be 8 mm and not less than 1/3 of the longitudinal bar diameter. E. Vertical spacing of ties shall not exceed 200 mm, whereas the spacing close to the joints within a length of 1/4 of the clear height shall not exceed 100 mm. Preferably, the spacing of ties shall not exceed the thickness of the jacket or 200 mm, whichever is less. Column strengthening is achieved by increasing the column section for the entire height, and a cage of additional main reinforcement bars with shear stirrups is provided right from the foundation as per the requirement of additional load. The longitudinal reinforcement usually is concentrated in the column corners because of the existence of the beams and passed through the holes drilled in slab and by placing new concrete in the beam column joints. Typical cross-section of column with jacketing is shown in Fig 4.6. Figure 4.5 Reinforcement detail of foundation showing strengthening. 4.4 Reinforced concrete strengthening of columns. Jacketing is one of the most frequently and popularly used techniques to strengthen reinforced concrete columns. With this method, axial strength, bending strength, and stiffness of the original column are increased. Reinforced concrete jacketing improves column flexural strength and ductility. Jacketing serves to improve the lateral strength and ductility by confinement of compression concrete. The common practice for interface treatment consists of increasing the roughness of the interface surface and applying a bonding agent, normally an epoxy resin. Closely spaced transverse reinforcement provided in the jacket improves the shear strength and ductility of the column. The minimum specifications for jacketing: A. Strength of the new materials shall be equal or greater than those of the existing column. Concrete strength shall be at least 5 MPa greater than the strength of the existing concrete. B. For columns where extra longitudinal reinforcement is not required, a minimum of 12 billion Argentine pesos in the four corners and ties of 8 at 100 C/C should be provided with 135 degrees bends and 10 leg lengths. Minimum jacket thickness shall be 100 mm. Figure 4.6 Jacketing of column. In this project, based on the results of the analysis, some columns need to be strengthened. The column layout plan is shown in Fig 4.7. Figure 4.7 Column layout plan. IJERT 10 is 060069 www.ijert.org 178. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 5. Conclusions: 2 alternatives for structural systems have been studied for the proposed extension. A. RCC beam column frame system with RCC floor and roof slab. B. Steel portal frame system with steel beam/RCC slab at intermediate floor levels. Roofing consists of steel truss with asbestos sheeting. Based on the STID analysis of the above models and the model of existing building, following results are obtained. I average increase in vertical reaction at base for extension with RCC beam column frame system is 60% in comparison to the reactions for existing building alone. 2. Average increase in vertical reaction at base for extension with steel portal frame system is 23% in comparison to the reactions for existing building alone. 3. The increase in resultant moment in comparison to existing building is 68% for R.C.C extension. 4. The increase in resultant moment in comparison to existing building is 30% with extension in steel structure. Results of the structural analysis indicate that the extension with steel portal frame system results in lesser increase in design forces and would require lesser strengthening of the columns and foundation. Hence the steel portal frame is adopted as the structural system for the vertical extension. The strengthening is required for foundations and columns to support the increased loads due to vertical extension. The strengthening of foundations carried out by providing new foundation over the exiting foundation. The increased area for laying the new foundation is provided by excavating the soil around the existing footing and filling by PCC. Column strengthening is achieved by wrapping existing columns with a four-sided jacket of concrete reinforced with longitudinal steel and transverse ties. 6. Future scope. The topic of story extensions and consequent strengthening is very vast. To build a new structure on top of an old brings many issues that differ from a regular project. So it is beneficial if the designers have access to as much important information as possible. The most prominent thing that can be investigated more thoroughly is experiences from executed projects. It would be good for the designers to have access to an extensive collection of buildings with story extensions. The main information about structural system used, strengthening methods and important experiences could be stated for each building. If this collection of projects was large enough, and well organized, the designer could quite easily find one or several examples that were similar to the project at hand. Recent Technology and Engineering, IJERT, ISSN, 2277-3878, Volume 3 Issue 3, July 2014, 4 babar.saheboetal/International Journal of Research in Modern Engineering and Emerging Technology 5 Manual for Retrofitting of Existing Vulnerable Buildings. RI, DC. Draft Code with Complementary on Seismic Evaluation and Strengthening of Existing Buildings, IIT Kanpur. 6. Building Adaptation by James Douglas Heriot-Watt University, Edinburgh, UK. 7. Brotto, C. 2004, New Concepts in Renovating, Barcelona, Structure. 8. Craven, J. 2008, Adaptive Reuse of Older Buildings, The New York Times Company. 9. Jodidio, P. 2007, 100 Great Extensions and Renovations, Australia. 10. Al-Imrani, M. Engstrom, B. Johansson, M. and Johansson, P. 2010 Bernde Constructioner Del 1, Load-Bearing Structures Part 1, in Swedish, Division of Structural Engineering, Chalmers University of Technology, Göteborg, Sweden, 2010. 11. Allen, C. February 25, 2013 Professor in Geotechnical Engineering at Chalmers University of Technology. 12. Bergenad, C. 1981 Pabijnad, Story Extension, in Swedish, Lund Institute of Technology, Sweden. 13. Vertical extension of existing buildings by use of light gauge steel framing systems by Susan Bergston Luleå University of Technology Division of Structural Engineering Steel Structures Luleå, April 2005 14 Yin, R. 1994, Case Study Research, Design, and Methods, Saga Publications, Volume 5. 15. Beal, D. 2008. A Review of the Concrete Technology and the Design Aspects of Structural Capacity of the Brisbane City Hall. 16. Jodidio, P. 2007, 100 Great Extensions and Renovations, Australia. 17. Filden, B. 2003, Conservation of Historic Building, Oxford. 18. Alagasundaramurthy, P. 2002 Shear Strength of R/C Beams Wrapped with CFRP Fabric, Research Report, University of Kentucky, Lexington. 19. Bergenad, C. 1981 Pabijnad, Story Extension, in Swedish, Lund Institute of Technology, Sweden. 20. Blaschko, M. and Zilch, K. 1999 Rehabilitation of Concrete Structures with CFRP Strips Glued into Slits, Technical University of Munich, Munich, Germany. 21. Sergio K. and Sharma AK 2001. Strengthening of Reinforced Concrete Members Under Compression and Bending. Structures and Building Volume 146, pages 277-231. 22. Naunaji, and Chalhari Z 1999. Reinforced Concrete Repairs in Beams. Construction and Building Materials Volume 13, pages 195-212. 23. Mohammed H. Kuniada M. and Nakamura H. 2012. Strength and ductility of RC beams strengthened with steel reinforced strain hardening cementitious composites. Cement and Concrete Composites Volume 34, pages 1061-1066. 24 Guidelines for Retrofitting of Concrete Structures, draft published by JSCE, September 1999. 25 Seismic Retrofitting of Existing Building The Master Builder, Volume 3 Dr. H. S. Rao. August-September 2001. 26 Structural Audit of Existing Buildings I. H. Shah. 27 New and Emerging Technologies for Retrofitting and Repairs Dr. Gopal Rai. 28 Manual for Retrofitting of Existing Vulnerable Buildings. References 1 Handbook on Repair, Restoration, Condition Assessment, and Rehabilitation of RCC Buildings, Central Public Works Department, New Delhi. 2 Moffat, I. 1987. Method of Adding Additional Stories to an Existing Storied Building. December 29, 1992. USA Patent Application 842,572. February 3, 1987. 3 Analysis and Design of RCC Jacketing for Buildings by Vid Prakash C. Marlapal, P. J. Salunk, and G. Gore, International Journal of IJERT 10 is 060069 www.ijert.org 179. This work is licensed under a Creative Commons Attribution 4.0 International License.